Thanks very much for the introduction. What I'll be speaking about today is the cosmic dipole tension, and you would have heard about this from my colleague Marley yesterday. And the message I really want to communicate today is that the dipole tension as it stands right now represents a profound challenge to our current cosmological paradigm. Future surveys, however, are going to be rich in the information they offer in constraining the nature of this tension, but we have to first think about how we're going to prepare for the onset and the arrival of that data. So that's what I'll be talking about today. But first, a quick refresher, and again, you would have heard this yesterday, but just so we're on the same page. When we look at the isotropic CMB, we have to, of course, remember that imprinted on top of this is a dipole of 2 orders of magnitude larger than those underlying anisotropies. And the conventional wisdom behind this dipole is, well, our heliocentric frame of reference is moving through the universe at a speed of about 370 kilometers per second up there in galactic coordinates. Okay, so it's kinematic in origin and induces this temperature shift. Now, if you accept that that is true and that it is kinematic in origin, then there should be an analogous effect in other observables. And this is what was talked about in Ellison-Baldwin in their 1984 paper, and it's sometimes called the Ellison-Baldwin dipole or the cosmic dipole. And essentially, it is a dipole in the counts of galaxies across the sky. And the basic idea, again, is that if I have some galaxy survey, say with a luminosity function like this, and I cut at some limiting flux density, then sources ahead of us might be boosted past that limit because of Doppler beaming, right? Because of our motion. And then sources behind us in the reverse hemisphere might be deboosted below that limit. And so the net effect of this kind of to and fro is a dipole in source density of that form there. And if you take the value from the CMB, the 370 kilometers per second, you get that typical values are around 0.004, 0.007, but more to the point, it's a 0.5% effect. So it's subtle, but in principle, it is detectable if I have sufficient counts and sufficient statistics, which is what I'll be talking about today. Okay, well, this is about tensions, this conference, so where is a tension? Well, the way this consistency check with the cosmological principle works is that essentially the dipole I see in source counts should correspond in magnitude and direction with the kinematic dipole from the CMB, right? And so, okay, how did it look in 2002? Well, Blake and Wall's paper, this was using the NVSS Radio Galaxy Survey. They've got the amplitude there, or I've got the amplitude there in units of CMB amplitude. It looks reasonably consistent. But the growing picture today across the electromagnetic spectrum is that we see an amplitude which is somewhere between 2 to 3 times in excess. Now, I will say there's a spectrum of different results there, right? But the general picture today is that we're somewhere in this 2 to 3 times region across infrared, across optical, and across radio surveys. While the direction looks to be pretty consistent, it's the amplitude that is quite stubbornly in excess. So, of course, this begs the question, what on earth is going on? And perhaps we can talk a bit more about that today. So this tension challenges, obviously, our lambda CDM paradigm and begs more questions. How can we prepare ourselves for the next generation of galaxy surveys? What do we need to take into account? Well, I've sort of broken it down into 3 S's we can think about. Firstly, we've got systematics. Are we actually measuring what we think we're measuring? Or is there some other instrumental effect, or perhaps some other physical effect we haven't thought about when we're measuring the dipole, which is throwing off our inferences? What about survey strategy or design? Well, we can think about this in an information theoretic approach. How can we optimize the constraining power in our surveys to get the best measurement of the cosmic dipole? And lastly, statistics. Are there different frameworks which can help us in our ability to constrain the nature of the dipole, its amplitude and its direction, say, for example? So I want to talk about these 3 S's. The first one I want to talk about, though, is systematics. And in 2024, we did a study with a sample of quasars called Quire. Now, this was created by Story Fisher and collaborators in 2024. And it consists of quasars from Gaia DR3, right? And we thought, okay, let's do a dipole measurement. Let's see what's happening in the sample. If you just plot the source density distribution of quasars on the sky, obviously the most striking feature there is the underdensity near the galactic plane. And this is an optical survey, so the natural conclusion is that this is probably from dust and extinction around the galactic plane. Now, this is a problem for us insofar that we're trying to probe the change in source density due to our motion. And we don't want to obviously probe the change in source density due to dust, right? It was all right for Quire, though, because the authors, Story Fisher and collaborators, they included a selection function in Quire, and that just tells you the probability of observing a quasar on the sky given its position, and that accounted for the effects of dust. And because that was a probability, we could take that selection function, put it in our likelihood as part of our Bayesian procedure, and then go and fit a dipole. Okay, well, what did we get when we fit that dipole? As you're seeing there, as we make progressively larger cuts around the galactic plane, the direction of the dipole drifts towards the CMB dipole, the black star there, while the amplitude also drops. Now, those are 2 sigma errors that you're seeing there on the amplitude. So actually, we're still seeing something that is roughly just a little bit beyond 2 sigma in excess of the CMB expectation. The important point I want to extract from this, though, is that even though there was a selection function which was used to account for dust, clearly there still is an effect which was not accounted for. And I want to flag this and just say that this is an ongoing problem, and will be an ongoing problem for optical and infrared surveys. Dust will present an issue for measurement of the cosmic dipole. Okay, looking at something different now, pivoting to the radio spectrum, we also did a study on 2 radio samples you're seeing there. NVSS, the NRAO VLA Sky Survey, and RACS, the Rapid ASCAP Continuum Survey, at its lowest frequency. So you're seeing the same map that I showed you before, the source density map, but this time it's been smoothed over with a moving average. So you're seeing more or less the large-scale changes in structure. And you saw a similar plot to this yesterday in Marley's talk. So okay, we've got our mask there, we've got our sample, we can go and fit a dipole to this, right? That's exactly what we did. And so in NVSS, you can see the direction of the dipole is more or less consistent with the CMB direction. Perhaps the story is not as clear with RACS low, and there may be some indication that it's not consistent. We didn't quite see that in the Bayes factors. But the important point I really want to take out from this study is the effect of local sources. Well, what do I mean by a local source, and how can it affect measurements of the cosmic dipole? Well, what we did in this study is we took local sources up to a median redshift of about 0.04 from the 2-mass redshift survey, and cross-matched those sources with their radio counterparts in RACS and NVSS. We took those and removed them from the final sample. And what we saw was about a 10 to 15% drop in the dipole amplitude after excising those sources. The basic idea is that the L=1 moment in the lambda CDM matter power spectrum, or the clustering dipole, will influence your measurement of the overall dipole in the sample. Remember, we're trying to look for the kinematic contribution and not the clustering contribution. Okay, so you can see that effect here. The gray posteriors, that's what happens when you measure the dipole with those local sources included. The red and the blue for NVSS and RACS low respectively, that's what happens when you take out those sources. So you're seeing a 10 to 15% drop. And this goes to show that the pure kinematic interpretation of the dipole in NVSS or in RACS low or in any survey can only be an approximation because there is also a clustering contribution. And this begs the question, well, how we approach this for future surveys? Is clustering going to be a problem? And so we're looking to the future. In particular, we're looking to SKA, right? When SKA arrives, it will offer a wealth of data, a wealth of information for constraining the dipole. So we're working with some collaborators at the SKA team, and they've provided us with lambda CDM matter power spectrum injected mock maps. And you're seeing that mock map here for SKA, right? So it's roughly the southern equatorial sky with a galactic plane mask there. And again, as I want to stress, this will have an L=1 moment because of clustering, because of the lambda CDM matter power spectrum. And therefore, if I were to fit a dipole to that, well, I can constrain its direction and I can constrain its amplitude, but this is purely because of clustering. And I can see it points somewhere there in the sky. So that begs the question, what happens if I take that map add a kinematic dipole into it, and then infer the overall cosmic dipole in the sample. You can see what happens there. So basically, more or less, that clustering dipole which lies in the sample drags the posterior for the direction away from the kinematic truth, which would be the CMB black star there, and influences your measurement. So this goes to show that clustering in lambda CDM is going to be a problem for future surveys when we're trying to measure the dipole. And we have to think about how exactly we're going to account for that in the future. Obviously, with a larger clustering dipole amplitude, that would affect it more, but in this case, there is definitely a noticeable effect. Okay, pivoting slightly differently to one of the other S's I gave you at the introduction, survey strategy. So in a paper we published at the start of this year, what did we do? Well, we thought about things in an information theoretic approach. And so we took source count, sky coverage, and the position of the visible sky of the survey, and we thought about how does changing all of those things change the information level in a survey? What do I mean by information? Well, one metric you can use is the KL divergence, or the distance between your prior and your posterior distribution, as a way to indicate the information provided by a sample. So firstly, what about the position of the visible sky? In this mock example, you're seeing a small localized 40-degree mock survey, right? And what we're doing is sliding the position of that survey across the sky. And what you can see in the right-hand panel is that when you do it, the Bayes factor comparing a dipole to a monopole changes. And that Bayes factor is highest at something called the dipole equator, and it's lowest at, I guess, the dipole pole there. And that just tells you that where the change in source density is greatest, you get the greatest constraining power, right? Where it's the least at the poles, that ends up being the worst in terms of constraining a dipole. What about the source count? Well, take that 40-degree slice I showed you before and throw some sources at it. If you had 5.75 million sources, you can get the amplitude, you can get the direction, but one of the angle parameters is highly degenerate, as you can see there. You can, of course, throw more sources at it, but that's quite a large number of sources. But it more just goes to show you that you can do inference on small slices of sky. Okay, what about the sky coverage? Well, this plot is showing you that if I think about the information provided per source for a fixed number of sources, if I increase the radius of my survey, then I end up getting more information per source, more bang for your buck, if you will. Okay, what if we combine all of these things together? In this plot, you're seeing how the KL divergence changes as a function of the source count and the radius of my survey. And the basic idea is that you can imagine some survey as being on a line of constant information. So I would need 40 million sources as you're seeing up there, in a 40-degree slice, or an 80-degree slice with, say, something less than 10 million sources, and those would both have the same constraining power. They would both have the same level of information. So that's what we're trying to show you there. One interesting consequence if you take all of these things together is that you don't need a continuous survey to do inference. In fact, you're perfectly fine with having scattered patches, discontinuous patches of sky with about 7.5 million sources in there, and then recovering the direction of the dipole and recovering the amplitude quite well. So that's quite interesting in that we do not need a continuous patch of sky. What about some other systematic effects? So in this same paper, I've talked about a dipole so far, but what about the higher order multipole moments? So we also looked at that. Why did we look at that? Well, there was a paper by Abgari and collaborators in 2024, and they mentioned, or they raised the issue of mode coupling between different multipole orders. And the basic idea is that when you mask your sky and you fit spherical harmonic functions, there can actually be a mode coupling or power leakage effect between certain multipole orders. And they raised this claim because in a very famous sample, the Catwise 2020 sample, in terms of the cosmic dipole, you can see that that has a quadrupole moment. Less sources there, less sources there. A really strong L equals 2 moment. And they also made the claim that there are higher order multipole moments in the data. So they said, okay, well, because we're chucking out half the sky, perhaps there's an issue of mode coupling, which means that there's power leakage from higher multipole orders into the dipole, and that's biasing inferences of the dipole amplitude. So we thought in this paper, is there a way we can extract out the dipole and higher order multipoles in an unbiased fashion, right? Even on masked skies. That's exactly what we were able to achieve using an approach called the trace-free symmetric tensor approach. The basic idea is that I decompose my multipole into unit vectors, and those help me define my multipole. And you're seeing a map there in the top right with a dipole and quadrupole signal baked into it. And in those two marginal posteriors, you can see that we're able to extract the dipole and quadrupole amplitudes in sort of an unbiased fashion, even though we've chucked out half the sky. You can play the same game for octopoles, okay, the order above a quadrupole, and we can recover the dipole and octopole amplitudes even on a masked sky. You needed more sources here, however. You needed more information to constrain the direction of the octopole unit vectors, but nonetheless, it is possible. Okay, lastly, looking at statistics. What have we been doing so far in the last few slides that I've shown you? Well, we've been using a classic Bayesian likelihood-based approach, right? And if I use a Bayesian approach, I better well be able to write down a likelihood function, some specific mathematical functional form which tells me how probable is my data given my model and its parameters. So in this case, we use a Poisson distribution, basically, where the count in each pixel is described by a rate parameter of that Poisson distribution, and the value of that parameter changes on the sky. And it's got a monopole signal in there plus a dipole signal, depending on where that pixel is with respect to the dipole vector. But what if I didn't know L? What if I didn't understand the data generating process and there was some other effect in the data I wanted to account for? Well, as long as I can write down my functional form, which goes from theta to d, I can use an approach called simulation-based inference, which basically uses a neural network to learn the relationship between theta, your parameters, and your data. And this is an interesting approach because I mentioned the countwise sample before. Countwise has a strong quadrupole moment. We're not totally sure what's going on in the sample, but one possible issue that could be causing the quadrupole moment is that the photometric uncertainty varies over the sky because of the varying sky coverage, basically where Y spends more or less time looking. That could induce an Eddington bias-like effect, where I have sources scattering past my flux limit more, where the photometric uncertainty is higher along that kind of ecliptic equator, as you're seeing there. So, okay, well, we can write some function, we can write down a simulation, and we can simulate this effect, where basically we have, in different patches of sky, higher photometric uncertainty and less photometric uncertainty in other patches, and then see how that affects the source density. That's what you're seeing in this map here. And then can we constrain a dipole, given this map? Well, yes, we can. Here you're seeing a corner plot for a dipole fit, but notice here that there's no quadrupole term, there's no term which accounts for how the error changes as a function of sky position. This is all baked into the simulation-based process, basically us drawing sources from a distribution at the level of the function you're writing down in code. And you can constrain the direction of the dipole, you can constrain its amplitude really well with that approach. So possibly there is a chance for it to be used in the future in understanding countwise. So just wrapping up everything I've talked about today, the cosmic dipole tension represents a profound problem for lambda CDM and one that we're going to have to think about alongside the Hubble tension, right? Future surveys are going to be decisive and are going to offer rich information in constraining the direction and amplitude of the dipole. But we can think about the things we've got to think about in the future as involving 3 S's. So the first one is systematics. Are we measuring what we think we're measuring? Is there a clustering dipole contribution? Are there higher order effects due to a scanning law? So on and so forth. What about the survey design and strategy? Are there ways we can optimize the information in a survey and get more bang for your buck out of the sample? And lastly, statistics. Are there different frameworks like a simulation-based inference approach or a classic likelihood-based approach? Are there different frameworks which might better serve us in investigating the cosmic dipole? So all of these 3 things will be really important in constraining the dipole in the future. So I'll wrap up there. Thanks very much for your attention.
Hey, Are there any questions?
Thank you for a very interesting talk. The last point that you mentioned was with the systematic related to the quadrupole, and this, it seems that is quite key. Understanding that systematic, just because that could be a systematic that could affect the dipole at the same order, I suppose, as the quadrupole.
Yes, so it's definitely possible that because of power at the L=2 mode, when you fit a dipole, it ends up changing your inferences of that dipole amplitude. So like, totally with you, we're going to have to think about how to account for it.
Yeah, I mean, yeah, so not just leakage of the quadrupole into the dipole, but also just the dipole signature itself. It may be sensitive to the scanning systematic that you had.
Yeah, undoubtedly. That's potentially what we're seeing in Catwise. So it's sort of why we're thinking about how can we account for that at the level of the simulation, so that the simulation pipeline knows about the scanning law when it fits a dipole, and then doesn't make a biased inference about the dipole because of it, right? So previously, what was done in Catwise is the change in source density as a function of ecliptic declination was just corrected for with a linear fit in Segrist in 2021. And then you can fit the dipole to it, and you get an amplitude of about 0.014, which is 2 times in excess of the CMB expectation. It may or may not change doing this. We could get the same dipole amplitude out. It could be different. It's very preliminary at the moment, though.
Okay. So, but is it your feeling that you are able to control this systematic, like to the level that you need to?
I hope so. It's very preliminary, so I can't be too confident with saying yes, it is, but maybe in the future. Yeah. Yeah.
Okay. Any other questions?
Thanks for the interesting talk. So the variable depth in galaxy catalogs is absolutely fundamental when you're doing anything like photometric clustering and all that sort of stuff. And that sounds to be exactly what you're looking at with this Catwise catalog. So my question is just a clarification.
Yep.
How is your source catalog defined?
Right. Okay. So in the simulation or in the real Catwise data set?
In the real data set.
Oh, okay. So with Catwise, you've basically got your sample. You make a cut in the W1 magnitude and also a color cut to extract quasars, or AGNs rather. That's what was done in Segrist. And then you plot how the density looks over the sky. You mask out the galactic plane and you mask out regions of poor photometry. That's how you construct your sample.
Right, but I think that very first point is the crucial one, right? You start with a source detection, and that source detection is highly inhomogeneous, right? Because of variable depth of observations on sky, which is related to this observation error map that you had before. Now, if you choose a sufficiently bright magnitude cut that you're essentially saying, I want just something that is only ever going to be detected at hundreds of sigma from the background, then the assumption is that the magnitude limit part of my selection window is negligible. But you have secondary effects that come in whenever you have imaging, right? And blending plays a role at bright magnitudes and things. And you have saturation effects at bright magnitudes. All these things play a role. And I think that it would be very useful to pay very close attention to those sorts of systematics when you're generating your simulations. Because I think forward simulating the observation effect like you've described is 100% the right way to do it. And I think you're probably going to have to do that in every band, which is going to be a lot of work.
Yeah, that's a really great point. I'm totally on board with what you're saying. Ideally, we would, scrounge through and find every systematic which could affect the source density and put it into our simulation pipeline. Like, these are very preliminary steps in trying to achieve that, but I think could be moving in the right direction to really understanding the dipole in these samples. But yeah, I totally agree with what you're saying there. Yeah.
Cool. Thanks.
Any final questions? I'll ask you a question. Maybe you showed this, but so when you do your simulation-based analysis, do you get a different result to your likelihood-based one?
It's very preliminary, and I don't have a result yet for that, because I haven't actually taken the cat-wise real sample and put it through the SBI pipeline and compared it with the Bayesian likelihood-based approach. What I can say, though, is that if you just make a simulated map like this, using our simulation pipeline, not using the real data, and then feed that back through the SBI pipeline, as you're seeing there, you can constrain the dipole really well, and that's consistent with what you get with a likelihood-based approach. So it's working in the simulations. The question is, when we take it to the real data, are we getting the same thing? And that's sort of for the future, what I'm looking at, yeah.
Thank you.
Thank you.
All right, let's thank Oliver again.